pleasure to be here for this Indo-French seminar. So I would like to thank INRIA and Cedric Adjih for. So I want to today I wanted to share the work we have done with my former PhD student Benoit Marie and with Dimitrios Tsilimantos, and we have investigated a little bit how we can leverage the reinforcement learning for URLLC schedule. And then I will explain a little bit the deep reinforcement learning framework. And then I will speak about one of the proposals we have, which is called NOMA PPO for URLLC. In 5G, we have very strict constraints in terms of reliability, so 9.999% off. And there is a specific difficulty for the uplink communications from the devices to the base station. Why? Because we need the base station has no information about the buffer and the buffer especially and the channel of the devices, and has to coordinate the devices. So the traditional MAC protocols they fail to meet the URLLC requirements usually. May miss a lot of transmission opportunities because it is uplink. You don't take into account the strict latency constraints, and as soon as you have slotted based techniques, you have collisions, interference. So if I look at the literature on the MAC protocols for URLLC, we can distinguish ground-based protocols. In ground-based protocols, you have a base station that allocates the resource to the devices. The device then sends the packets to the base station. And you have ground-free protocols, and in ground-free protocols, we want to avoid the four-way on-check that we have traditionally in cellular networks. The four-way on-check is the fact that the device makes a random access to the base station, then the base station gives the allocation, then the device sends the packets, and then there is a hack. So there is a four-way on-check that takes a long time. That is not feasible in case of URLLC communications. So the idea of ground-free protocols is we avoid this four-way on-check. So there are two techniques. Either you are contention-free. So in contention-free, ground-free protocols, the BS pre-allocates the resource in advance. So you say, for example, every 20 milliseconds, you have one slot. This is pre-reserved, pre-allocated. So this is okay if the traffic is quite predictable. If it is not predictable, you lose a lot of opportunities and you lose a lot of bandwidth, so it's not a very good solution. The other solution is to have a contention-based ground-free protocol where you allow the devices to send to the base station, but you don't coordinate them really, and there might be some interference between the transmissions or some collisions, as we say when we work in the field of MAC protocols. Another trend in the research is the integration of advanced radio interfaces, or like NOMA, non-orthogonal multiple access, macro diversity, MIMO techniques, and so on. So how can they improve the MAC protocols is a question of research. So there are some challenges for the uplink of URLLC communications. In ground-based protocols, you have an inherent latency due to access and polling. This is an issue. In contention-based ground-free protocols, you have collisions. In collision-free ground-free protocols, you have to pre-allocate, so you lose in terms of flexibility. And there are specific difficulties like device heterogeneity. So if imagine that not all devices have the same constraint in terms of latency and reliability or data rate. You have dynamic environments, so you may have varying traffic models, varying channels, and a number of devices. And there is the question of how to fully exploit the advanced radio techniques at the physical layer, at the MAC layer. So what we have done is we have explored some reinforcement learning solutions. So reinforcement learning is a big domain. So there are some drawbacks, there are some advantages. Okay, we'll see together. So we have investigated how we can leverage the advantages of reinforcement. So now, if I look at reinforcement learning, we can again classify the schemes. You have a single agent reinforcement learning. So in single agent, you have a single decision maker that makes the decision in the network. So usually you have to deploy this at the base station. And in the literature, it has been heavily used for ground-free like protocol. For example, you can adapt the transmit power. So this is a kind of actions you can take. Adapt the transmit power, adapt the number of retransmission, decide which uplink resources will be used and so on. So there are some challenges which are the partial observability, as I said. So what is partial observability? The fact that you don't observe the state of the system. You don't know, you just have some measurements or past informations, okay, delayed information. And protocol overhead, because you have the base station has to poll at least devices. So an alternative is to go to multi-agent reinforcement learning. So now you have different, it's like a game a little bit. You have different agents, decision makers. So probably they are deployed in the devices, and every device takes its own decision. So here it can be appealing because it can be, it's scalable. You can deploy this kind of solution in a decentralized way, so it is appealing. But if you look in the literature, there are some challenges. So most of the time we implement independent learning. So what does it mean? It means that we just reuse single agent reinforcement learning protocols, algorithm, and we deploy just in the devices as if the environment were stationary, which is not the case. Okay. So as you lose stationarity, why it is not stationary? Because the other agents, they also learn the environment and they take also decisions, so the environment is not stationary. So you lose all the guarantee that you can have with single agent reinforcement learning. So this is a limitation. Another approach is centralized training and distributed execution, built on the fact that in many use cases you can learn together offline and then deploy the network and act in a decentralized manner. So this is a possibility, but this usually what we have observed is the fact that this kind of techniques lack of scalability. So what is the deep reinforcement learning framework? So the classical framework, you might know it, you have one agent, so one or several agents, so let's start with one agent, and repeatedly you take some action, and these actions they have an influence on the environment, and from the environment you retrieve the state of the environment, and you get a reward. Okay, so this is a classical Markov decision process framework also, and what we try to optimize, it's a sum of rewards. Okay, so it's a sequential decision problem. The classical function is the value functions. So this value function starts in a state S0, and then you take you apply some policy. So the policy is noted by here. So the policy is just taking an action when you are in a certain state, and then the system evolves according to a transition function called T here that depends on the state and the action. And over the time, you try to maximize the sum of rewards. So at every state, when you are in state S and you take action A and you transit to state S T plus 1, you get this reward R. And usually, to avoid theoretical complexities, we use a discount factor, gamma, which is less than 1, and which put more importance on the immediate reward compared to the delayed reward. So if we are in a multi-agent reinforcement learning problem, we have something similar, but we are more in the game. Here we are talking about the policy pi I, okay? And the other agent, they have a policy pi minus I, and now you have to optimize with respect also to the decision of the other agents. So in the classical MTP framework, you can solve this problem, quite easily if you assume that, for example, you are looking for Markovian policies. So Markovian policies depends only on the state where you are, and policies can be stochastic, so it means that you take decision with a certain probability, or they can be deterministic, means that for every state you have a single action. Okay, so there are classical techniques like value iteration, policy iteration to find pi. But classical, in many systems, the state and the action, or even the action space, can be so large that it's not possible to run this exact algorithm. We have this so-called curse of dimensionality, so it's too large to be solved. So in deep reinforcement learning, what we will do is the fact that we will parameter, we look only at the optimal policies, but in a subset of all. So, and this subset is defined by, for example, a neural network, so a set of parameters. So we parameterize the policy. So the several type of algorithm in reinforcement learning. The well-known Q-learning look at not this value function, but the value of taken one action and then following the best policy. Okay, this is the Q function. Depends on the action you take and the state where you are. Okay. And if you have all these QAS values, you just have to take the argmax and you have the optimal policy. So the Q-learning and all the algorithms that are based on the value function, they try to estimate this Q function. There is another family of policies that try to directly optimize the policy. And all they are more or less based on the policy gradient theorem that said that if the policy is parameterized by a certain parameter theta, we have a nice expression, nice, I don't know, but okay, quite nice expression of the gradient of this function seen as a function of theta. Okay? So we can express it as a function of the policy by theta that we are looking at, okay, and of the return of along a trajectory. So what is a trajectory? It's a sequence of few wheels, okay, and according to the transition of the environment T and the policy you are following by theta, okay. So you follow this policy, and along this policy you have an expression, a nice expression of the gradient of this function, and so with gradient ascent you may try to find a local optimal of the value function. So there have been several algorithms that have been proposed based on this idea, but the first ones, let's say, had some drawbacks. First, the return creates a high variance. When you have a high variance, it's more difficult to learn. So here the idea will be to introduce some kind of bias, so some kind of unbiased baseline in the objective. This is the first approach. There is also the first algorithm. They are on policy learning. So what is on policy learning is the fact that if you want to improve a policy, you have to run some samples with this policy, and then you improve. And if you improve your policy, you have to run new samples. Okay, and all the samples you got before, they are not useful anymore. Okay, so it's better to have usually algorithms that are off policy learning, in the sense that you can run a policy but still improve on another policy. Okay, that is not the same that you are running. So this is something that yeah.
What is the return?
The return is the same return as we spoke before. This is the reward.
And the reward.
Okay, and the return is the sum along the trajectory of the instantaneous reward. Another difficulty with policy gradient algorithm is the fact that sometimes if you change a little bit the parameter theta, you may see a high difference in the policy. So it's an issue when you try to learn, because you may jump from very different performance in terms of value function. So one big steps has been achieved by this 2015, this algorithm, TRPO. So this is a trust region policy optimization. So they have derived from the policy gradient theorem this maximization problem, where we see that they try to optimize a certain surrogate objective function. So I don't go into the details of how they derive this, but we can remark that first you have it's off policy learning. So this is why we have here pi theta and pi old. So it means that it's coming from the principle of importance sampling. So it means that you can run samples with the old policy and still improve over the pi theta. And another thing that is appearing, it's the advantage function here, ASA. What is advantage function? It's just the difference between the Q function and the value function. So value function we have C. The Q function also is the reward, the long-term reward you can achieve if you take action A instead S. And the advantage function is just the difference between the two. Okay. So this is a trick to reduce the variance problem we have seen before. Okay, instead of looking at the return, you look at the average advantage you have by taking one action over the average action, because VS is what you can get with the average action, while QAS is what you get if you take action A, and AAS is what you gain over the average action. Okay. So it looks like a bit obvious, but the idea is to reduce the variance. Instead of having a very high variation of the value function, you have only the difference with the average action, so it reduces the variance. And it is, we can show also that it is unbiased because the value function does not depend on the action, and so we don't have any issue on this. So the authors, they have said, okay, if I change a little bit the data, I can change a lot the policy. So what we will do is we will constrain the change in the policy. Okay, so a very simple way to do it is to use the Coupechoux difference. Okay, that as a constraint to say, okay, I can maximize over theta, but I don't want that distance between the two policies are too high. Okay, so I put a constraint on this. So this protocol has been quite successful, but it has again some drawbacks. In the fact that this maximization problem is not that easy to compute, and it's a bit computationally intensive. So proximal policy optimization has replaced, in fact, this constraint by what is called a clip function. So it's very simple. We take the mean between what we wanted to optimize and this function, this clip function, times the advantage function. And the clip just say that, okay, I don't want this ratio to deviate more than some parameter. Okay, so it's very simple. So we just remove in this way the constraints, and we have some advantages. So this PPO seemed to us a very good candidate for URLLC scheduling for several reasons. So it's less computationally intensive than TRPO. It's quite flexible in the sense that we can work with discrete or continuous action space. We can work in fully or partially observable environments. So, as I said, if you know perfectly the state here, you are in a fully observable environment. But if you don't have the state, you have only observations, you are in the framework of a partially observable environment. And one advantage of PPO is that it can work easily in this framework. Recently, we have seen that PPO has been was not the best one, but until so far it has been very good on the classical benchmarks, which are, for example, the Atari games, so it has good performance, and it can be extended to multi-agent reinforcement learning by using IPPO, so independent PPO. So we deploy PPO in every device. What we have observed is the fact that the performance is highly dependent on the implementation details. So it's not me, my students worked a lot on the code and discovered that just implementing the theoretical PPO is not sufficient. Okay, you have some tricks in the implementation that can change a little significantly the performance. So we have to take this into account, and maybe we have to think about that there are some theory. I mean, in reinforcement learning, we noticed that there are some theoretical foundations, but there is a lot of heuristics here. It's like have a global framework which is theoretically grounded, let's say, but then when we go for practice, small tricks are very important. And so maybe the reason of the success of let's have a look at what we have done. So we have considered a single agent reinforcement learning. Okay, so it means that we have a base station and the devices that should send the packets within 1 millisecond with a high reliability. And the reinforcement learning agent is in the base station. So we avoid the for-free uncheck protocol because what we will do is the fact that the PS will poll the users, okay, and the user will send the packets. We allow collisions and we rely on NOMA to reduce the number. We have two main limitations. The first thing is the fact that we have a combinatorial action space. So this is the particularity of this problem, let's say, compared to, for example, Atari games or something like that. And we have partial observability because we don't know which device has to send.
If base station is polling, then why they are collision?
There can be collision because we'll allow the base station to poll several users for two things. The first thing is the fact that we use NOMA. So in NOMA, you can transmit, thanks to successive interference cancellation, you can transmit simultaneously to the base station. And the second reason is the fact that we want to gain information from the users. Because when they will contact the base station, they will send some information that is related to their buffer or to their channel. And so we learn about this.
And so every device has a PPO agent, or it is not?
No, the PPO is only in the BS. Okay. Only in the BS. Okay. So the two challenges are the combinatorial action space and the partial observability, as I said. So combinatorial action space, why? Because if you have n users, you have 2 power of n possible actions. So it's exponential set. So how can we deal with this? In the literature, we have found continuous reinforcement learning. So it means we will project the discrete action space on a continuous action space, and then we will treat the action space as continuous. But in our case, it's not that obvious in which space we have to project the discrete action space. So we have not investigated this. You have sequential prediction. The fact that you predict, you try to learn the first dimension, then the second dimension. So there is sequential learning about the action dimensions. Okay, but here we don't. One of the drawback of this is the fact that you should have an order, a predefined order. Otherwise, it can be random. So it's not very clear which order you have to choose. We have a branching architecture. I will come back on it. That has been proposed because we relied a little bit on this. And for partial observability, if you look in the POMDP theory, the basic approach is to work with belief states. So you don't know in which state you are, but you have a probability distribution over the states. Okay, but working with belief states assume that you know the model. Or in reinforcement learning, you don't know the model, you don't know the Markov chain transition and so on. Otherwise, you have recurrent neural networks. Okay, we have tried also this, and generative models we have not so investigated. Recurrent neural network is a traditional way of dealing with partial observability, but we had problem to introduce some prior in this case, so we have not considered this. So this is the network model. We have so we try to be a little bit realistic, in a sense, but you can judge. So we have time frames. We have a downlink slot during which the PS polls the devices. Okay? So it's what is the action space? It's 0-1 vector of the dimension k. And while polling the device, you allocate some pilots. Then you have a guard band. Then you have the uplink transmission. So all the poll devices that have a packet becomes active, and they send their packet together with a pilot for the channel estimation, and they send also some buffer information. Then we have a guard band, and then we have the downlink ACNAC that is required to know if, for the devices to know if they have to retransmit or not the packet. So we allow retransmissions within a strict deadline. We have taken typical values from the TPP because we have assumed 40 megahertz of bandwidth and I think 30 kilohertz of subcarrier spacing. And so we have we have taken one WFDM symbol for every slot. And so we have realistic timing here to compare to the 1 millisecond latency.
K is the number of devices.
K is the number of devices.
Yeah,
it is known and it is fixed. So if I look at the channel, we have, very traditional model with large-scale scaling, fast fading, thermal noise, with several antennas at the base station, one antenna at the devices, and we have introduced some process for the fast fading. okay, that follows this Gauss-Markov model, classical Gauss-Markov model, which depends on this AK correlation coefficient that itself depends on the speed of the user. Okay, I say this because the coherence time of the channel play an important role in the learning process. Then we have introduced some seed decoding procedure. So the idea is that is the following: we receive the signal, we have eta, which is the set of received signal. We have U of t, which is the set of active users that transmit the packet. We have a hard constraint as it is proposed by most of the paper in the literature on NOMA. So it means that if there are more than B user transmitting, there is anyway a collision and cannot retrieve the signal. If it's not the case, we compute for the first user the SINR, okay, assuming that the other signals are interference, and we compute using the finite block regime in information theory. We compute the probability of error of this data, okay, and then we draw with the binomial solution this packet has been decoded or not. If it has been decoded, we remove this user from the interference of the successive users, the other users, and if it is not decoded, we keep it in the interference term. Okay, and we do that for all the active users. So at the end, we have a SINR, which is useful signal on interference noise. Interference is made of all users that are decoded after user K and all users that have not been, that are before user K, but the base station didn't manage to decode the packet. Okay. In terms of traffic model, we rely on two 3GPP model. The first one is a probabilistic periodic traffic. So the idea is the fact that every device sent with a certain period, possibly with a certain probability. So there is an offset for every user, which is, for example, for user 1, F1, and then every NP, so it's a number of frames, possibly it can send a packet with a certain probability. And we see also on this diagram that after a delay delta 1, which is a strict deadline, the packet is lost. There is another traffic model that is called probabilistic aperiod traffic, which is only a Poisson process. It's very smart. What we have seen is the fact that this one is more predictable and it's quite easy to be handled by the learning algorithm. But the Poisson is more difficult because it's, finding discernible patterns in the Poisson process is a bit more difficult for the learning algorithm. So for the buffer, we have this process. So imagine that this is the buffer of user K, and we have in this table we have several entries, and each entry corresponds to the time to deadline. So, for example, there are 2 packets with a time to deadline of 1 radio frame. There are 0 packets with a time to deadline of 2, and so on and so forth. Okay. So if device K send a packet, and this packet is successfully decoded, then you see that we have still 1 packet with a time to deadline of 1, and the rest they stay the same. They remain the same. And then at the next frame, we'll increment this table. So this one will be lost because it's too late, and the other one they just jump by 1 step. Okay. So for example, this 0 comes in the first place, this one comes in second place, and so on and so on. Okay, so we just move the buffer. And if you have a new arrival, so it means that, for example, you have time to deadline of 4, so you have 1 new packet here in the buffer. Okay. So we distinguish for the learning algorithm the observed buffer. So this buffer has been sent, it's a successful transmission. So this buffer information has been sent to the BS with the uplink packet. So the BS knows exactly the buffer status at that time. We have an estimated buffer, so the BS can estimate that at the next frame the buffer will look like this. And we have the real buffer, which includes also the new arrival, something that the BS is not aware of. Okay, so we distinguish this. So what we want to do is, what is the optimization problem with this model, is to optimize the URLLC score. So URLLC score is it's a packet error rate, and just different way to say it, but it's packet error rate. I mean, the idea is the fact that we want to combine the reliability and the latency constraints in one score. Because if you if you don't meet the latency constraint, you just lose the packet, so you will decrease your URLLC score. So this is the idea. So we want to find the policy pi that maximizes this sum reward. Here we have phi k, the probability to decode user k at time t with the discount factor, and we have the evolution of the system that is concerning the buffer, okay, which is so the buffer is evolving according to a certain transition function, and the channel is evolving according to a certain transition function also, as we have seen. So the PMDP formulation is the following one. We have a state. The state is made of the buffer, the receive power, and the observation. What is the observation? It's the polling decision you have taken at time t-1. The packets you have managed to successfully decode at t-1, the observed buffer at t-1, the observed channels at t-1, and the reward. The actions we have already seen, it's a vector of k dimension. And we have the history, which is classically the successive action and observation we had since the beginning of the system. And we have the reward function that we define like this. The reward, when we are in state S and we take action A, it's just the number of packets we have successfully decoded. So in the literature, sometimes there are people are including some penalty when there is a collision, for example. If there is a collision, I had a penalty on the reward. So here designing the reward is a bit expert dependent. I mean, there is no real theory behind this, except that you think about your optimization problem and you design an immediate reward that corresponds to this optimization problem.
Marceau, you mentioned something about the coherence time.
Yeah.
Do you think that somehow related?
Coherence time is included in the evolution in the transition function of the. So as I said, so some people include some penalty for collisions. We have observed that first does not bring so much. No, it does not bring anything in fact, and it prevents also the learning algorithm to test because even if there is a collision, you gain information. For example, if I pull two devices and there is a collision, I know that these two devices they have packet in their buffer. So I gain information, and we don't want to prevent this kind of situation. So to deal with the combinatorial action space and the partial observability, we have defined an agent state. It's a bit similar to a belief state, but definition is different. At each frame, we define the estimated. We see the estimated buffer. I mean, we gather the estimated buffer, the estimated channel receive power, and a certain number of time informations. The last time the device has been active, so it means polled and it has packet, and also the last time that it has been successfully decoded. So we take this agent state and we show that in fact this agent state is Markovian first. So this is interesting for the next proposition. And also, what is important is it's a sufficient statistic for the action observation history. So you can, what does it mean? It means that the probability to be in state S knowing the whole history is exactly the probability to be in state S knowing the agent state. And of course, the dimension of the agent state is much lower than much smaller. Okay. So it's a bit reminiscent for those that know POMDP. It's a bit reminiscent for belief states, because we know that belief state is a sufficient statistic of the history, but it's not a belief state in the sense that we don't have here a probability to be in state. We have just gathered the necessary information to summarize the whole story. And an important thing is the fact that we have, with this agent state, transformed the POMDP into an MDP. And so we have transformed the problem of partially observable to fully observable. How to deal with the combinatorial action space? So the idea is the fact, so it's taken from this branching architecture that has been proposed by this reference in 2018. And the idea is to have in the policy network one branch per device only. Okay, And then so one branch per device will provide a probability of activation of every device. Okay? And then we will add some hidden layers to combine and to take into account the interdependency between these branches. Okay, so we have an architecture that grows only linearly with the number of users, and we try to take into account the interdependency with the shared information, shared layers between the branches. So this is the idea. So this idea does not come from us. We just have adapted to our case, and without going into the details, there are some that should be found in the architecture between the autonomy of the branches and the fact that we have to coordinate them in a sense. Okay. To be short, if you put too much neurons branches and not on the coordination, you will lose the coordination, and otherwise you will lose also you will lose on the complexity side. Another trick we have introduced to deal with the partial observability is Bayesian policies. So the idea is to use a prior, which is expert-based. So we know that some policies could be good. So we include this in the policy we are looking at, in the set of policies we are looking at. Okay. So for example, we know that the EDF scheduler is optimal in many simple case, homogeneous case, and so on. So it's a good scheduler. So EDF means that we just poll the user which has the packet which is the most urgent. So we take this into account as a prior, and we also take into account in the channel, we include the channel prior in the sense that probably bad channels, we should not hold people with a bad channel. So for example, if the receive power is less than a threshold and this information is not too old, so I know that the channel was bad and it's not too old compared to the coherence time, so then I deactivate this device. I don't want this device to be polled. And so we construct a posterior policy, which is the policy given by the network times this prior. So the EDF scheduler is an oracle because you don't know the buffer, but we can implement the prior based on the estimated buffer, and this is what we do. So we have the estimated buffer, we construct the EDF scheduler. So at the end we have algorithm. You start with a given policy and a given value V. Then you run with the posterior policy, you collect a certain set of trajectories. So it means that you run your policy for several trajectories. Sorry, I don't see 5 minutes. Okay. You compute the rewards to go. So it will give you an estimation of your value function. You compute the value function using a value network. Then you can compute the advantage function. You update the policy with gradient ascent, so you find the new data, and then you update the value network by minimizing the mean square error between the return you have along your policies, your trajectories, and the value you have, the value function that is parameterized by the parameter phi. So this is the structure, and some of the results are shown here. So here we have 18 users. You see on the x-axis is the episode. So the training is done offline. Then you operate the network online, but it's very quick. But what is long is the offline. So here you have time. Here you have the URLLC score, and we have compared to several benchmarks. So there is a traditional deep Q learning, okay, which we have adapted to NOMA, but which failed to converge, in fact, because of the combinatorial problem of action space. We have a multi-agent deep Q learning IDRQN NOMA, so we have adapted. So it gives quite good performance, but less than what we have proposed. We have also BDQ, which is another protocol that uses the branching architecture, but fails to deal with the partial observability. And we have deactivated agent state or prior to see the influence of these features we have added. And in our case, we largely, beat the benchmarks in terms of conversion rate and objective function. If I look at so this is the URLLC score as a number of devices for the probabilistic periodic traffic, and this is for traffic. So here you have at the top you have the EDF scheduler, but this is an oracle with respect to the buffer, so cannot be implemented. It's just a benchmark. In red we have our proposal, And here we have the different benchmark where we see that, we beat quite easily for the various regions I have said before, so that IDRQN does not converge after a certain number of devices. PQ cannot manage the partial observability. Slotted LOA is not even aware of the URLLC constraints, and so on and so forth. Something I wanted to show you also is the influence of the coherence time. We have two convergence of the URLLC score shown here. On the left, you have the long coherence time, and here you have a short coherence time. So if you have a long time, you have time to learn the channel. And if you have time to, we have compared NOMA PPO with no CSI. So this is the curve here. EDF, which is here, and NOMA PPO with full CSI and NOMA PPO. So here we see that full CSI and NOMA PPO have approximately the same performance. It means that the protocol, the algorithm is able to learn the channel. It is interesting to see that we even beat EDF, because EDF is aware of the buffer. It's an oracle with respect to the buffer, but not with respect to the channel. So you can even beat EDF if you have time to learn the channel. But if the coherence time is small, like here, you cannot, you see the difference. If you have no CSI, you reach a lower value. If you have full CSI, you have the best value, but it's like an oracle. And if you have our scheme, you are in between. Here, EDF is better. And NOMA PPO, full CSI, and EDF are converging, which is a good thing in terms of learning of the buffer. It shows that the algorithm is well learning the buffer. Okay, so the contributions are the following. We have introduced this agent state, which is a sufficient statistic for the past history, and which allows us to convert the PODP into NDP. We have enhanced PPO with the branching policy and biagent policy, with this branching architecture, and we have outperformed the traditional MAC, in these 3GPP models. If you are interested, we have other approaches in terms of URLLC scheduling for the uplink with still deadlines. So filter PPO is more adapted to periodic traffic and use. SecDQN and MCA PPO are two multi-agent reinforcement learning for the same problem. Okay, as I spoke here, but without, this one is not for NOMA. It's a classical framework, let's say. And this one is for multi-channel access. So all the references are in the presentation. Probably the slides will be available. Okay, thank you for your attention.
Long live India and France friendship.